So this is part 3 of this section of substitutions, and we just call it miscellaneous substitutions. If you've already noticed, our goal when we're using substitutions is to basically change a DE that was in terms of y and x into a DE that's in terms of u and x. So let's keep that in mind on this first example. So here's our first example. Here's a DE, and it tells us the substitution to let u equal x plus y. Well, we're going to have to find dy dx and substitute for that. So let's take the derivative of both sides. We'll go ahead and do it in terms of x, since we want dy dx. It's 1 dx dx plus 1 dy dx. So solve for dy dx. 1 from both sides, really. So replace dy dx. We can see x plus y on the bottom becomes u. And if you factor out a negative, we have another u. So let's change that. Well, shall we see if it's separable? So integrate both sides. And then back substitute equals x plus y. If we want, we can clear a fraction. And we don't need to distribute that too, obviously, because it'll get absorbed into that constant. A note here is this original problem, could have also been done as exact. It's in your homework. It's a good exercise to do it, a different method. So on this one, since we have e to the y, we're going to let u equal e to the y. We're going to try that. Take the derivative with respect to x. Solve for dy dx. Make sure that looks like a u. Replace it. Replace our u's. E to the y. U. And it looks like if we didn't replace this, or replace that with u, it's going to cancel. So that will cancel with that. Or change them to u's, they still cancel. I don't think it's going to separate, but it looks like it's a prime candidate for integrating factor. But let's get it into the right form. I'll have to divide everything by x. Our integrating factor, u. Multiply through by your integrating factor. Now rewrite this as a product. Check. Yep. Looks like it matches. Works. Integrate. And with respect to x. Solve for u. Back substitute. Solve for y. Have to take the natural log of both sides. And that's our solution. So here we have a second order differential equation. First time we've solved that, but we are in a chapter that's linear. So our goal is to reduce the order of it by some substitution. So if we let u equal y prime, take the derivative with respect to x of both sides, we get this is our substitution. Let's plug it in. So y prime is du dx. So y double prime is du dx. And y prime is just u. And y prime, that's u squared. Since we have u squared, what are you guys thinking of? Maybe Bernoulli? N equals 2? Try it, but we're not in the right form of it. So we're going to subtract the linear one over. And we also got to get rid of that at the same time. So Bernoulli, definitely n is equal to 2, but we've already used u. Can use w. So we need to solve for du dx. Solve for it. Substitute for it. So if you remember, we're going to divide by that each term. Might as well get rid of that negative while we're at it. Now we can use our w. So we use both of them. Okay, so integrating factor again. Pretty interesting problem, huh? So since I cleared out my negative, we're already, this is my p of x. So I'm going to multiply through by my integrating factor. Rewrite this. Let's check product rule. Yep. I don't need to write that. Yeah, we can see those cancel. It's just w. Now let's backpedal. W is u to the minus 1. Let's get rid of that x. So this is our original substitution, u equals y prime. So this is 1 over u. So it's 1 over y prime. So if we want to take the reciprocal, probably want a common denominator. We don't need that 2 there. It gets absorbed. So now we find y prime. Just reciprocate. Reciprocal, reciprocal. But remember, our solution is y, not y prime. So let's integrate now. That is y. Oops, let's use white. And here we are going to have to sub-index this because we're going to have another constant. Remember second orders? We're going to have two constants for second orders. Here's my C2. Put back in that V. And this is my general solution. Again, we just solved our first second order. So we have two constants for a general solution. Cool problem, huh?